Okay, so space figures is the topic, specifically volume and surface area of space figures. And space figures take 3 dimensions of space to represent a figure, so you can't just represent it on a flat piece of paper without kind of trying to, put in some tricks of the eye there. One important group of space figures is Polyhedra. These are space figures where the faces of the figures are made up of polygons, which we just finished studying. As we go through this morning, remember that you can type questions into the chat bar. There's a little bit of a delay between when I talk and when it actually gets to you. So, I'm not ignoring you. And feel free to interrupt at any time. Okay. So here's some of the names of the regular polyhedra. Remember how we had regular polygons where all the sides were the same length? And similarly, we have regular polyhedra where the faces, so on a space figure that's a polyhedron, you have vertices, which are at the corners, where 2 edges meet, or 3 or 4 or whatever. So here's an edge, and here's an edge. And then we have the flat surfaces, like this triangle here in the front of this little pyramid. This is called a face. And so if the face is a regular polygon, and all the faces are the same, then we get these regular polyhedra, also referred to as Platonic solids after Plato. So tetrahedron would have 4 equilateral triangles. Hexahedron would have 6 squares. It's really a cube is what we call it in everyday language. An octahedron has groups of 4 regular triangles. That's in green there. A dodecahedron has groups of 3 regular pentagons, and that's in purple. And then an icosahedron, groups of 5 regular triangles. Now there's only certain shapes that will come together in this special way. In general, the categories of space figures that we're primarily going to be concerned about are on this slide. We're not going to be concerned about a torus, but we're going to be looking at pyramids. So let's talk about what constitutes a pyramid. For a pyramid, you can take any polygon as the base. So if you draw a polygon, and then imagine that's the bottom of this 3-dimensional object, and then you just put a point above the polygon and connect it to each of the vertices of the polygon, then what you get is called a pyramid. So you'll see the pyramid in blue there. It has a square base, and then the pyramid next to it has a pentagonal base. And then they both come up to one little point at the top. Anything of this shape, with these characteristics, I should say, that has a polygon at the base and comes up to a point, that's a pyramid. Compare that to prisms. So prisms have a base like the pyramids do. So it could be any type of polygon. Let's just make a square. Okay, so the difference is, instead of coming up to a single point at the top, you draw the same shape at the top as the other base, and you just connect them. Okay, so here, this would be an example of a rectangular prism. It has rectangles in the top and the bottom. Here we have a triangular prism in green, and a pentagonal prism in purple there. But you can have any polygon as the two bases, and then you just connect them and it's a prism. And the way we find, for example, volumes of pyramids is going to be slightly different from how we find volumes of prisms. And then of course we have the case where we have a circle involved. So we still can build a pyramid that's got a base that's a circle, but we don't call it a pyramid. We call it a right circular cone. This has a right angle, by the way, formed by the line segment connecting the center of the base to the top point there. And then same thing here, right circular cylinder. We have two circles being connected. It's a kind of prism, but we don't call it that because the base is not a polygon, it's a circle. Okay, so these are the basic categories of shapes that we're going to be working with. All right, and what we're going to be measuring, because we're always interested in measurements of these objects, is the volume and the surface area, as I mentioned before. The volume is the measure of capacity of a space figure. It's how much space it fills up, and the volume is measured in cubic units. So another way of writing cubic units, by the way, is units to the power of 3, units cubed. Is 3 is not a coincidence. This is a direct result of these being three-dimensional objects, and we're measuring them in a three-dimensional way. How much space? You can literally imagine cubes, like ice cubes, and we're counting how many 1 by 1 by 1 cubes fill up a space, and we're going to talk about that shortly. Surface area, on the other hand, is the total area that would be covered if the space figure were peeled and the peel laid flat. So this is like wrapping paper. We want to know how much wrapping paper it would take to cover a certain object. The surface area is an area, and remember we said area is always measured in square units. Okay, so let's first start with the basic object that we first learned to find the volume of, which is a box. Remember we said that volume, we're trying to count how many 1 by 1 by 1 cubes fit inside of the box. So here I have a box that, remember, is also called a rectangular prism, and it's 4 by 6 by 5. So what I'm going to do is I'm going to start by trying to figure out, breaking the box down into layers basically, and figuring out in each layer how many 1 by 1 by 1 cubes are in that layer. So if we had a slice of the box that was only 1 unit high here on the left, then imagine filling the box with cubes that are 1 by 1 by 1. Since the front dimension is 6, we could fit 6 cubes across the front, and we could fit 4 cubes down the side. So if we were to continue this, and fill the whole thing up, how many cubes would fill this one layer? Well, there would be 4 times 6 equals 24 cubes, or 24 cubic units that would fill the one layer. But how many layers do we have in the 4 by 6 by 5 box? We have 1, 2, 3, 4, 5. And each one of those layers has 24 cubic units in it. So 4 times 6 times 5, or 24 times 5, is 120 little cubes that would fit inside of this rectangular prism. So what we had to do in the previous slide was to multiply the 3 dimensions together to get the number of cubes. So the formula for volume is length times width times height. Now the surface area is a lot different from finding the volume. Oops. Actually, we'll come back to the surface area in a minute. Let's go ahead and find the volume of this box, and then we'll talk about the surface area. All right, so to find the volume, we said you just use volume equals length times width times height. So in this case, the length is 7, the width, which kind of looks like it's going into the screen, is 2, and then the height is 3. So multiplying, oops, I don't want to do that. So multiplying those together, we have 7 inches times 2 inches times 3 inches. So 7 times 2 is 14, times 3 is going to be 42. And then inch times inch times inch is inches cubed. So if we were to imagine filling this space with little tiny 1 by 1 cubes, there would be 42 of them. Okay, now let's talk about surface area. So in order to visualize surface area, sometimes it's good to draw what's called a net. And so in this case, imagine that this thing's constructed out of cardboard and we're going to unfold the box, right? So I'm going to label this front as side 1 and this as side 2 and the top as side 3. So what I'm going to do is I'm going to draw side 1, and then I'm going to imagine that I have broken open this box. Side 3 would be up top if I laid it flat. Laid it, like if it's a cardboard box and I take it and I break it apart and side 3 is still attached to side 1, then side 3 would be up here somewhere. Side 2 would be over here. But we're missing some other sides, right? How many other sides do we have? Well, underneath the bottom, let's call that side 4, there's going to be something. But also behind the box, there's a back, right? Let's call that side 5. And then also there's another side over here that would be let's say the left side of the box, which we can't see in this drawing, and let's call that side 6. So there's 6 sides altogether to this box. So if I've broken it apart and folded it open, adjacent to the front of the box, side 1, on the bottom we've folded out, there's side 4. And then adjacent to side 3, the back of the box, side 5, would be back there. And then there's also this left side sticking out over here from side 1. We called that 6. So there's 6 sides to this box, and this is called a net, what I just drew out there. All right, so when we talk about surface area, we're talking about trying to find the area of this cardboard that's been all spread out on the floor there. Okay, so let's talk about the dimensions then of this box. So remember, we have a length L, a width W, and a height H. And you can see very clearly, for example, that side 2 has dimensions WH, but also side 6 is right across from it, so it has dimensions WH as well. So if we wanted to find the combined area of just piece number 2 and piece number 6, the sides of the box, we'd have side 2 is H times W, and side 6 is H times W. So add those together, we have 2HW. So this, in this formula for surface area that you see right here, this is the sides of the, oops, yeah, that's right, sides of the box there. Now, the front of the box has dimensions L by H. So side 1, we have L and we have H. But the back of the box is directly across from side 1. It has the same dimensions as well. Remember, the back was side 5. So this is LH as well. So the area of each of these is L times H, and we have 2 of them. So this is going to represent the front and the back of the box has that area all together. And then the only thing left is the top and the bottom. The top is side 3. And so look at side 3, we have a dimension L and a dimension W. So L and W. And side 4 on the bottom also L and W. So this right here, 2 times LW, represents the area of the top bottom. Okay, so that's where this crazy long formula for surface area comes from. We have 6 different rectangles that we have to add up the areas for. And so if you just remember that you do the top and the bottom, the front and the back, and the 2 sides, then you can keep track of your surface area. So let's go to the specific example. Okay, so finding the surface area. Okay, we have the front and the back. So the front has dimensions 7 by 3, 7 times 3. So the back does as well. So we're going to have 2 of those. So 2 times 7 times 3. And then we're going to do the sides. The order in which you do this doesn't matter, but we have a right side and a left side, and they both are 2 units by 3 units. So the sides are going to be 2 times 2 times 3. 2 times 3 is the area of each side, but we have 2 of them with those dimensions. And then the top and the bottom, the bottom you can see has dimensions 7 by 2. So the area of the bottom is 7 times 2, but the area of the top is as well, so we're going to double that. So the surface area is going to be, and sometimes we'll denote it SA for surface area, sometimes it'll just be S. But the surface area is going to be 2 times 7 times 3 plus 2 times 2 times 3 plus 2 times 7 times 2. I'm just going to check to make sure you guys are still with me. I'm going to type in the box, the chat box. Okay, so keep in mind order of operations, multiplication comes before addition. So we have 2 times 7 is 14, times 3 would be, what would that be? 14 times 3 would be 30, plus 12 would be 42. Okay, good. You guys are still with me. So 2 times 2 times 3 would be 4 times 3, which would be 12. And 2 times 7 times 2 would be 14, times 2 would be 28. 28 and 12 is going to be 40, plus 42 would be 82. And then it's square inches, because remember, we're finding an area here. Okay. So that's how you find the volume and surface area of a rectangular prism, which is just a box. All right, if it's a cube, then this simplifies things tremendously, because cubes are boxes or rectangular prisms where all the dimensions are the same. So instead of having length times width times height, you have S times S times S, or S cubed. And instead of the surface area being the double of the front and the back, the double of the 2 sides, and the double to get the top and the bottom, each side is just going to have an area of S squared, and there are 6 sides, so we get 6S squared. So if all the sides are equal, it's actually easier. So if I asked you to find the volume of this cube and told you that all the dimensions are 5 feet, then you would find the volume by cubing 5, and that would give you 125. Notice the dimensions for volume are always cubic units. So 125 cubic feet. And then the surface area would be 6 times 5 squared, because each side has an area of 5 squared, or 25. And there are 6 sides, so that would give us 6 times 25 is 150 feet squared. Again, surface area is an area. So the units are always squared. Okay. Let's talk about how we would find the volume of prisms in general. We did a box, which is a rectangular prism, but we can also do any kind of prism in a similar way. So when you're finding the volume of a prism, what you're really doing is you're multiplying the area of the base times the height. To see that this is true, let's go back to this guy here. So notice that when we were looking for the volume of this particular box, we looked at how many cubes would fill one layer. And it turned out that in this 4 by 6 by 5 box, there were 4 times 6 equals 24 cubes filling the bottom layer, which happens to be the area of the base, right? The area of the bottom of this box would be 4 times 6 equals 24. And then we just multiplied that number times the thickness of the prism, because we have 5 of those layers. 5 times 24 gave us our total volume. So really, the 4 times 6 part could be thought of as the area of the base. We use a capital B for that, area of the base. And then the multiplying by the height part, H, is just multiplying by the number of layers. The same thing will work no matter what kind of rectangular prism we have. I'm sorry, what type of prism we have. If we have some way of multiplying or finding the area of the base, then all we have to do is multiply that times the number of layers to get the volume of the object. So in general, the volume of a prism is capital V equals capital B times H, where capital B is the area of the base. All right. The same thing works too if you have remember I said when the base is a circle, we don't call it a prism. You could, but we just refer to it as a circular cylinder. But the same idea applies. We could find the volume of one slice with a height of 1, which is just the area of the base, capital B, and then multiply that times the number of slices, which is the height. So you see here where the volume is equal to pi r squared times h. That pi r squared is just the area of the base. The area of the base is the formula for the area of a circle, right? The area of a circle is pi r squared. So the area of this base is pi r squared, and then we just multiply that times h to get the overall volume. So we have these slices that are 1 unit thick, and we add all of them up, and we get the total volume. Now you will have access to the volume formulas during your test by clicking on the link to the ebook. But if you understand that in the case of all types of prisms, even circular cylinders, you just need the area of the base times the height, this formula is not hard to remember. We'll talk about the surface area in a minute and where that comes from, but first let's go ahead and calculate the volume of a circular cylinder that has these dimensions. So this 2 is the radius of the circular base, and this 10 is the height of the circular cylinder. So if we want to find the volume of this guy, we just multiply pi times the radius squared, so 2 squared, times h, which is 10. So the volume is going to be 4 times 10 is 40 pi. This is the exact volume. And the units would be meters cubed. Because it's volume, we would put meters cubed. Now, if I wanted an approximation of the volume, I would ask you to use 3.14 for pi, and you'd plug it in and get a decimal approximation. Okay, by the way, since pi is about 3, we're looking at about 120, more than 120 cubic meters here. All right, let's go back now and figure out where this surface area formula comes from. So to get the surface area, we will add up the area of all the sides if it happens to be a prism. But when you have a circular cylinder, the area of the sides is a little harder to visualize. You still can visualize it by drawing a net. So in our net, we're going to have the top, which is a circle, and the bottom, which is a circle. And then in between, imagine if you took an aluminum can, cut down one of the sides, and spread it out. So what you would have is the sides of this guy would fold outward, peel away, and you'd end up with a rectangle. So this would be the net for a circular cylinder. Now the dimensions would be h, would be the dimension from the height of the cylinder, but we're going to have to put a little work into figuring out this dimension here. And then we do also know the radius of each of the circles. So to find the surface area involves adding the area of the top plus the area of the bottom. And then we need the area of this rectangular region that's connecting them. Now, since we got this rectangular region by peeling it off of these circles, this distance here is going to actually be the same as the circumference of the circle. And how do we find the circumference of a circle? Well, if we're using the radius, we're going to use 2 pi r. So this distance along the edge of this rectangle is actually 2 pi r. And this is really all the information we need to get the surface area, because the area of the top circle is going to be pi r squared, and the area of the bottom circle is going to be pi r squared, because they're circles. And then the formula for a rectangle, length times or base times height, or length times width, however you want to think of it, the area here is going to be 2 pi r, the length, times the width, which is h. And if we add these up together, then we're going to get the formula here for surface area. So this piece here is going to be the area of the rectangle. And this is 2 times pi r squared, because we have the area of the two circles, the top and the bottom. So that's where that formula comes from. All right, so let's go ahead and use it. So here we have S equals 2 pi RH plus 2 pi r squared. Just want to repeat, if you forget this formula, you will have access to it by clicking on the ebook. Practice using that at home. And then we will have S equals, in this case, 2 pi times r, which is 2, times h, which is 10, plus 2 pi times r squared, which is 2 squared. Make sure to observe correct order of operations. So, you know, the exponent comes first, and then any multiplication, and then addition. So we're going to have 2 times 2 times 10 is 40 pi, plus 4 times 2 is 8 pi. Treat the pi like it was an x. So 40 pi plus 8 pi is just going to be adding the coefficients, 48 pi. And then what are the units on surface area? The units in any area are square units. So this one would be meters squared. this is the exact surface area. If I wanted you to give me an approximate surface area, I would ask you to use 3.14 for pi and then give me a decimal approximation. Okay, so that's how you find the surface area of a cylinder. All right, let's talk about pyramids. Remember the difference between prisms and pyramids. Pyramids have a polynomial base, and then they come up to a point, a vertex at the top. We previously learned how to find the volumes of prisms where you have the same shape on the bottom and the top instead of coming up to a point. For a prism, remember, we just found the base, the area of the base times the height gave us the volume of the prism. It turns out that when you find the volume of any pyramid, it's just going to be 1/3 that amount. So let's use this idea. We're going to find the volume and surface area of the pyramid. And you'll notice there's no formula for the surface area of the pyramid. You're just going to have to figure it out by adding up the areas of all the sides. But let's start with the volume, because we just said the volume of any pyramid is 1/3 capital B, the area of the base. Remember, capital B means area of the base, and then times the height. All right, so in our diagram, when I'm talking about the area of the base, this base happens to be a rectangle. So a rectangle, you find the area by multiplying the length times the width. So that's going to be 6 times 3 equals 18 square centimeters. That's the area of the base. But we want the volume. So we're going to say volume equals 1/3 times 18 square centimeters times the height, h is this 7 centimeters here. Okay, now the order in which you multiply the numbers doesn't matter. I noticed that, remember, when you take 1/3 of something, that's the same as dividing it by 3. So 3 goes easily into 18, so that's nice. So 1/3 times 18, a third of 18 is 6 square centimeters times 7 centimeters. That means the volume is 6 times 7 is 42. Centimeters squared times centimeters to the first power would be centimeters cubed. Or you can just remember that the volume always has cubic units. All right, so that's how we would find the volume of this guy. Oh. You know what, actually, I think we're not going to do the surface area on this slide. Let's skip that for now. All right. Now there is a formula for both the volume and the surface area of a sphere. A sphere is a ball shape, right? It's hard to visualize sometimes, but it's a three-dimensional circular shape, right? So it's coming out at us from the screen here. The only dimension you need to figure out the volume and surface area of a sphere is the radius of the sphere, which is the distance from the center of the sphere to any point on the outside of the sphere. So the volume of a sphere will always be 4/3 pi r cubed. And the surface area turns out to be 4 pi r squared. We're not going to go into where those come from because those are a lot harder to develop. You need calculus. So let's look at this example. If you were asked to find the volume and surface area of this sphere, you would say, write down volume equals 4/3 pi r cubed, right? That was from here. And the surface area is 4 pi r squared. Okay, so let's go ahead and calculate. We are given this one dimension, that's all you need, that's your radius. So your volume is going to be 4/3 times pi times 9 cubed, 9 to the 3rd power. All right, so exponents come before multiplication, so let's go ahead and find 9 to the 3rd power. So you can just either multiply 9 times 9 times 9 3 times, or usually most calculators have an x to the y button, so you could say 9 to the power of 3. So you get 729. So we have volume equals 4/3 times pi times 729. And now let's deal with the 4/3 times 729. On the TI-30X2S calculator, there's actually a fraction key where you can just literally type 4/3 times 729. Not the pi part, you have to leave that part by hand, but you can multiply the fraction. But it's not too hard to do with a regular calculator if 3 goes evenly into 729, because here's what you do. You think of the 729 as being 729 over 1. So that means your volume is multiplying fractions, you multiply straight across. So you'd have 4 times 729 all divided by 3 times 1, or 3. And we'll just have this pi being multiplied at the end there. So let's see, we can either divide the 4 by the 3 or the 729 by 3. Not both. You only distribute the division if there's an addition in the numerator, but there's not. So let's go ahead and just see if 3 goes into 729 evenly. 729 divided by 3 is 243. So we're going to get volume equals 243 times 4 times pi. In other words, 3 goes into 3 once, 3 goes into 729, 243 times. So then we just multiply 4 times 243. And we get 972 pi. Okay, and then what are the units? Well, it's volume we were finding, so it's always going to be cubic units, in this case cubic inches. Now this is the exact value of the volume. Again, if I wanted an approximation, I would ask you to put 3.14 in for pi. All right, let's try and find the surface area now. So the surface area is how much paper it would take to wrap this sphere up. So we're going to say surface area equals 4 times pi times the radius squared, 9 squared. So that's going to be 4 times 81 times pi. So that's going to be 324 pi. And the units, since we're talking about area, will always be square inches or square meters or whatever, units squared. So that's how you find the volume and surface area of a sphere. Remember, if you have any questions about how I found any calculations, don't hesitate to ask. I can always go back to it. Okay, so here's an example directly out of my math lab. It's a pretty challenging example, so this exercise gives people a lot of trouble, so I wanted to make sure to talk about it in class. So a plane intersects a sphere to form a circle as shown in the figure. So what they're saying is we have this ball, and if you can imagine slicing, taking like, I don't know, a sheet of metal and slicing through the ball here, then where it slices through it forms a circle. It says the distance from the center of the circle to the center of the sphere is 3 inches. And that's what they've labeled here, this distance here, 3 inches. If the area of the circle formed by the intersection is 16 pi inches squared, so this is the area of the circle, what's the volume of the sphere? Okay, so I'm going to erase the sheet of paper or whatever that's slicing through so we can just focus in on the sphere and the circle. Okay, so they're asking us to find the volume of the sphere. Do you remember the formula for the volume of a sphere that we just saw on the previous slide? The volume is 4/3 pi r cubed. So what's the only dimension we need in order to find the volume of the sphere? The only dimension we need is the radius of the sphere. Now, we don't have the radius of the sphere. We have a distance from the center of the sphere to whatever this circle is where we've sliced through the sphere. We would like the radius of the actual sphere. We don't have it. So we have to think about how does the radius of the sphere relate to the information that we do have. Hold on just a second. Sorry for the interruption. Okay, so what I was saying is, what's the relationship between the radius of the sphere and these dimensions they've given us over here in the diagram? The relationship is that if we draw a segment from the center of the sphere to the point where the circle touches the sphere over there, that would be a radius, but it's also the hypotenuse of a right triangle. So we have a little bit more information. We have a relationship that maybe we can work with. So the technique that we're going to use to solve this problem is we're going to find the radius of the circle. The radius of the circle would be this distance here. And then we're going to find the hypotenuse of the right triangle that I just described, that's formed by connecting the endpoints of the marked line segments. And then we're going to use that radius to find the volume of the sphere. So here we go. First step, find the radius of the circle that's formed by the intersection of the sphere with the plane. How can we do that? What other piece of information do we have that relates to the radius of a circle in some way? They didn't give us the radius of the circle, but they did give us the area of the circle. And what is the area of a circle always equal to? Pi r squared. So they're telling us the area of this particular circle is 16 pi. So if 16 pi equals pi r squared, then it must be that 16 is r squared. And what number can you square to get 16? You can square the number 4, right? So the radius of the circle must be 4. All right, now next, so that's step 1. We found the radius of the circle. Now we're going to use that to find the radius of the sphere, because here we have a right triangle, right? And we know by the Pythagorean theorem that if you square each leg of the right triangle and add that together, you get the hypotenuse squared. A squared plus b squared equals c squared. So that would be 3 squared plus 4 squared, that would have to equal the radius of the sphere squared. Remember, this is a different r from over here. This was the radius of the circle. Okay, and what I'm talking about here is the radius of the sphere. All right, so that would be 9 plus 16. That would be equal to the radius of the sphere squared. And 9 plus 16 is 25 equals r squared. What number can you square to get 25? The number 5. So our radius of our sphere must be 5. So that was step 2. And then step 3, use the information from item 2 to identify the radius of the sphere, that's what we just found, and use the radius to find the volume of the sphere. Remember, the volume of the sphere is 4/3 pi r cubed. So let's find that. Volume equals 4/3 pi times the radius cubed. It's going to be 4/3 times pi times 5 cubed. Now 5 cubed is 125. So the volume of the sphere equals 4/3 times pi times 125. Think of the 125 over 1. 3 does not go evenly into 125, so we're just going to multiply straight across. 4 times 125 is 500 over 3 times pi. This would be the exact volume of the sphere, and we would need to put in the units though. So it would be, volume is always cubic unit, so it would be 500 over 3 times pi inches cubed. And this is a perfectly fine way to write your answer. Okay, so we did step 3. Any questions about this one? I know it's probably not something you would think of these steps on your own, so that's why I wanted you to see this one worked out. Okay. So here's all the steps worked out on your slides. All right, now we're going to go and look at the volume and surface area of a right circular cone. We already, let's see. It doesn't matter. All right, so this one has a really weird surface area formula, and I want to explain to you where that comes from. The volume of a cone is exactly what you would expect, because remember, this is a pyramid. It's just got a circular base. So how did we find the volume of any pyramid? We took 1/3 the area of the base times the height. In this case, since it's a circular base, the area of the base is pi r squared. So that's where that volume formula comes from. Now, I'm not going to go into all the details on the surface area, but I do want to explain that where this weird square root of r squared plus h squared in the formula comes from. If you were to find the length of the side here of this pyramid, notice that it's exactly the hypotenuse of this right triangle that's formed by the radius and the height. And so if you were to set up the Pythagorean theorem to find side C, you'd have r squared plus h squared equals c squared. So it turns out this side C, which is also called the slant height of the pyramid, well, I should call it right circular cone, is actually the square root of r squared plus h squared. So this portion here is the area of the slanty part of the object, and then this pi r squared, of course, is the area of the base. So you don't need to know where the surface area comes from, but I just want to, I think the insight helps you to remember what formula this is and why it's associated with this shape. But again, when you take your test, you're going to have access to the ebook and the formulas. Okay, so let's take a look. It says find the volume and surface area of the cone below. So the first thing you're going to need to do is to use the formula for the volume of a cone. So remember, volume is 1/3 pi r squared h. Okay, so all you need to do is to identify the radius, which is 3, and the height, which is 4. And plug in and make sure you observe correct order of operations. So the volume is going to be 1/3 times pi times 3 squared times 4. So that means the volume is 1/3 times pi times 9 times 4. 9 times 4 is 36. And you can think of it as 36 over 1. Multiplying, we have 1 times 36 is 36. 3 times 1 is 3. So you have 36 over 3 times pi. 36 divided by 3 is 12. So you have 12 pi. And then you just put on your units, which is cubic units. Okay, so that's how you find the volume. And now let's find the surface area. So you remember the surface area formula. We have pi times r times the square root of r squared plus h squared. And then we have pi times r squared. Surface area equals pi times r times the square root of r squared plus h squared plus pi r squared. Okay, so again, we need our r and our h, and that's it. We just plug in. So we have S equals pi times r, which is 3, times the square root of r squared, 3 squared, plus h squared, which is 4 squared, plus pi times r squared, which is 3 squared. So let's see what we get. S equals, we're going to have pi times 3 times 3 squared is 9 and 4 squared is 16. So under here we have 25. Square root of 25 is just 5. Plus pi times 3 squared, which is 9. So we have S equals 15 pi plus 9 pi, which is just going to be 24 pi. You just add up the coefficients. And what are the units? So since it's surface area, area is always square units. So 24 pi m squared. Okay, got a little cough this morning. All right, so that's the end of this section. So are there any questions at all? All right, if not, we're going to end the live chat there. And remember that you can always send me your Ask My Instructor questions. Your midterm exam, if I recall correctly, is due in a week. And so between now and then, you can send me your questions. You can go to the STEM Center. The STEM Center is on the first floor of the library if you go towards the left in the back. And there are tutors there that can help you. Remember, I posted a schedule so you can go when there are tutors for the Math for Liberal Arts. That's what you want to look for. Math for Liberal Arts tutors are tutors for MGF courses. Remember, there's not going to be any one chapter that is emphasized more than the others. We have a range of topics, so you don't have to know everything. You don't have to get a perfect score, but you need to know, a good variety of the topics that we've learned. Remember to bring your calculator. Remember to bring your ID. If you haven't made an appointment yet, you need to go ahead and do that. There's a link in the announcements. It's going to have set theory, it's going to have logic, and it's going to have geometry. All right, it's really important to prepare well for this midterm. It's worth a lot of points. Also, the first 3 chapters, set theory, logic, and geometry, people tend to find easier, actually, than the last 3 chapters. The last 3 chapters are counting methods, probability, and statistics. And so, don't count on, I'll do better on the final. You need to score as well as you possibly can on this midterm. Remember, there's a practice midterm that's posted in my math lab. So it's very similar types of questions that you're going to see on your actual midterm. So you want to practice that as much as possible. If you don't have time to practice it in my math lab, remember, it's not graded. It gives you bonus points, but it's not graded. So if you don't have time to do it in my math lab, you can always just submit it, get a 0 on it, and then go into the grade book, and you have the option of printing it out so you can study it that way. And you could always take the printout to the STEM center or to a tutor or to my office and get help with anything that's giving you trouble. So now is not the time to give up. Now is the time to get stubborn. Okay? So use all your resources. Read your book. You'd be surprised how much you gain from reading the book. Watch your videos. Remember, there are bonus videos posted in the My Math Lab homework. And then email me your questions. So good luck, everybody. Study hard. And I'll see you on Monday or Tuesday, depending on when your class is, and we'll start an entirely new topic.